Ladies and gentlemen, welcome to the final session on option valuation, in which we are going to go through an introduction to option Greeks. Well, option Greeks are called so because we use Greek letters to represent what we represent. So essentially what we want to do is to study the impact of a change in a variable on the values of a call and put option. So what are the variables then that can impact the values of a call and put option? Well, we have already come across these variables before, and they will include the stock price, the strike price, which also is known as the exercise price, the time to expiration, the standard deviation of stock returns, and the risk-free rate. We are not including, and we have not included in the entire framework, the dividends paid by a stock. So please remember that in this discussion, in this particular course, we are using non-dividend paying stocks. The scheme that we are going to follow in this session is that we will allow these variables to increase and see how the option values respond. Of course, if we allowed these variables to decrease, our conclusions would be opposite. Well, this means that once we know the impact on an option price of increasing these variables, we already know the effect of reducing these variables, because they will just be the opposite of what would have happened when we increase the variables. So what I'm going to do is I'm going to switch to my writing tool, and we are going to talk about the impact of these variables on the values of call and put options. Okay, so let's talk about the impact of the variables that we have identified on the value of call and put options. Let us begin with the first variable, which is the stock price. So I'm writing stock price here, and which is denoted by S in this particular chapter. And we are saying that if the stock price increases while all other variables remain the same, so that's an important assumption, all other variables remaining the same, what would happen to the call price and the put price? So as a shortcut, we can remember that if the stock price increases, the call value will increase and the put value will decrease. Why that is so, we can verify that very quickly. So let's do a very quick verification here. Let's use the call valuation formula here. It's equal to S times N of D1 minus the present value of the exercise price times N of D2. So now it's very easy to see here that if this value of S here increases, the natural effect of that is going to be that the call value will also increase. And if you look at the put options formula, which we arrived at by modifying the put call parity condition, we wrote C, which is the call, plus the present value of the exercise price minus the stock price. Now in this case, if we increase the stock price, what is happening? This item S is being subtracted from this whole thing, and if we increase the value of what is being subtracted, then that will result in a smaller number as the final result. So as a result, the value of the put option is going to fall. Ladies and gentlemen, whether an increase in the value of an option or a fall in the value of an option, you must know that any change which is experienced by the option value as a result of a change in the stock price is known as its delta, and its Greek letter is this, delta. For a call option, ladies and gentlemen, we already know how to compute a delta. When we computed the N of D1 in the example that we took in the previous video lecture, that at that point in time we had actually computed the delta. ND1 is the delta of a call option, and the delta of a call option, ladies and gentlemen, is close to 1. This delta is close to 1 for a call option which is in the money. You will surely remember what we mean by an in the money call option, something which will be profitable to be exercised immediately. And what kind of an option that will be? For a call option, the S minus E will have to be positive to keep it in the money. So when the S minus E is positive, you will find that N of D1, which is also the delta of the call option, will be close to 1. Otherwise, if the call option is out of the money, the delta or the N of D1 will be close to 0. So let's write that here. It's close to 0 for an OTM call. So ITM call and OTM call. Let's move further and talk about a put option here. So what is the delta of a put option? So for a put option, delta of a put is going to be equal to N of D1 minus 1. Whatever you get, you will take its absolute value. So the absolute value of ND1 minus 1 is going to be the delta of the put option. So the absolute value of this item is going to be close to 1 for an ITM put, in the money put, which will be the case when the E minus S is positive, and it will be close to 0 for an OTM put, out of the money put, when the E minus S is 0. Right. In the question that we solved, when we found the call price to be equal to $10.74, we did that in the previous video. We had computed the N of D1 there, and if I recall correctly, the N of D1 was equal to 0.9772. What this means is this is the delta of the call. What this means is that if the stock price goes up by 1 unit, the option price is also going to go up by 0.9772 units. And if the stock price falls by 1 unit, the call option will also change by 0.9772 units. For the put option, the delta is going to be the absolute value of 0.9772 minus 1, and this is going to give us an absolute figure of 0.0228. So you can see that for the put option in this case, the delta is fairly close to 0. Let's move further. Let's talk about the time remaining to maturity. So if the time remaining to maturity increases, all else remaining the same, all else is same, what is going to happen? Well, consider an option, well, may that be a call option or a put option, and think about it as an OTM option at the moment, out of the money. It's not profitable to exercise it at the moment. If its maturity date is tomorrow, think about it. If its maturity date is tomorrow, it is likely to expire that way. It will remain out of the money for whatever time remains. Anyway, very little time remains because the maturity date is tomorrow, and it is just going to expire just like that, out of the money, in an unprofitable condition. But on the other hand, if there is still time remaining, let's say 6 months are there to go for expiry, there is a good chance that the stock prices might change in a way which will make the option profitable to exercise, and thus it will become in the money, or ITM. We know that an ITM option, in the money option that is, has a positive intrinsic value. Therefore, greater the time to maturity, greater the chance of an OTM option to become ITM. Therefore, greater the time remaining, greater the value of a call as well as a put option. It also means, therefore, that as we draw closer to maturity, the time value will fall, and on expiry date, the time value will be 0. The change in the option value as a result of a change in T is known or denoted by the Greek letter theta, and it is written as this, theta. So this represents the change in the value of an option as a result of a change in the time remaining to maturity. Ladies and gentlemen, we just noted that as we draw closer to maturity, the time value falls, and on the expiry date, the time value is 0. This is why the options, may that be a call option or a put option, they are called wasting assets. Wasting assets. Why that is so is because their time value reduces or wastes away with time. Well, you will remember maybe from the first session, we said that the total value of an option, which I'm writing as TV, total value, this TV is not time value, this is total value. The total value of an option is a sum total of its intrinsic value, IV, plus the time value. So this time I'm writing the full word, time value. I didn't write the TV because otherwise there might have been a confusion. You have a TV on the left hand side and you have a TV on the right hand side. What is the meaning of what? So the total value of an option is a sum total of intrinsic value and time value. Therefore, it is very much possible for an option to have a 0 intrinsic value but still sell for a positive price because of a positive time value. So even if this item is 0, but the option still has time remaining to mature, it will still carry some positive time value, which will mean that it will have a positive price for which it will sell in the market. In the example that we solved in the last video, we had this data, if I remember correctly. We had the stock price equals 45 and we had the exercise price equaling $35. So given this information, if you think about the intrinsic value of a put option, what would it be? So let's write the intrinsic value of a put here. It will be a maximum of two numbers, either 0 or E minus S. So if we just put in the numbers, what do we see? Maximum of 0 or 35 minus 45. So that will give us a maximum of 0 or minus 10. So clearly the intrinsic value out of 0 and minus 10, 0 is a bigger number. So we say that the intrinsic value is 0. But then you will remember that we had gone on to manipulate the put call parity to compute the put price, and the put was selling in the market for 6 cents. So what do you attribute this 6 cents to? This 6 cents is nothing but the time value because the intrinsic value is 0 anyway. Likewise, if you think about a call option now, what would be the intrinsic value in the same example of a call? Intrinsic value of a call is equal to a maximum of two numbers, 0 or S minus E. So if we plug in the numbers, what we observe is that we have a 0 and S minus E would be 45 minus 35, which would give us a comparison between 0 and 10, and we have to pick up the larger number. So the intrinsic value of this call option would be $10. But when we computed the option price using the Black-Scholes model, we found that the call option was selling for $10.74. So clearly 74 cents would have been the time value. Time value is 74 cents for this call option. Right. Let's move ahead and let's talk about the standard deviation. So what will happen if the standard deviation of the stock returns increases, all else remaining the same? All else is same. No other variable is changing. So ladies and gentlemen, I would like to assume that you know this, that standard deviation denotes risk, because an increase in the standard deviation means greater variability in stock prices, and more variability means a greater chance of profit or loss. So when we think about risk, it is not only the negative thing that can happen, a risky thing could be very profitable too, because there is greater variability, there are more ups and downs. So, well, if there are downs, then there is also a possibility that it could go up. So there's a greater chance that way of ending up in a profitable situation, but at the same time the possibility of loss will keep on lingering as well. In the case of options contracts though, the loss we know is limited to the premium that we pay for an options contract, and the profit potential still remains unlimited. This is a very good situation. So no matter how much the risk increases, our loss is not going to exceed a certain limit. We said before that there is a floor to which floor to the loss. There is a limit to how much we can lose, and that limit is the amount of option premium that we pay. Therefore, what will happen in this case is that if the standard deviation increases, it will only increase the upside for us, and that will cause the value of both the call and the put option to increase. So greater the standard deviation, so standard deviation rises, risk rises, and because we are already protected against the downside, it is limited to the amount of premium that we pay. The unlimited upside is going to cause the value of both the call option and the put option to increase, because this is a good thing for us. Of course, the opposite is true as well. If you reduce the standard deviation, then the call value as well as the put value will fall. Ladies and gentlemen, the change in the options value in response to a change in its standard in the standard deviation of stock's returns is known as an options vega. The Greek letter used is vega. This measures the change in the value of the option as a result of a change in the standard deviation of the stock's returns. And it is written like a V. I'm trying to create that thing, vega. This is a Greek letter, vega. All right, let us move ahead quickly. Let's think about the risk-free rate of return. The risk-free rate of return R, if it increases, all else remaining the same, what's going to happen? Let us consider a call option. Consider a call. Let's write the call valuation formula. It's equal to S times N of D1 minus E times small e to the power R times T times N of D2. So you see, the more times you write it, the easier it is to remember the formula. Now think about it. If you increase the R, here is the R, and R here acts as the discount rate, because we are discounting on a continuous basis, and for discounting purposes we need a rate, and this is that rate. If we increase the discount rate, what is going to happen to this entire second term? Whenever we increase the discount rate, the value of this term will fall. Isn't that so? So once this value falls, we will be subtracting a smaller amount from the first term. This is the first term, this is the second, this is the first term, this is the second term. So if the second term falls, then we are subtracting that much lesser from the first term. So what is the result? What will happen to the value of a call? The value of a call will increase in response. Now think about a put option. A put option is specified as C plus the present value of the exercise price minus the stock price. Now if you increase the discount rate here, increase the value of R, what's going to happen? It is going to make the second term, this term, smaller. When this term becomes smaller, this will mean that we are going to be adding a smaller term to the first term, which is the C. So we will be adding a smaller value to this C, which will mean that the final result, which is the put option, will experience a fall. So the put option will experience a fall. So I can't get the arrow, the down arrow here. So the put option will fall because the second term is getting smaller, and because the second term is an additive term, so we are adding that much lesser to the first term, making the put value lesser as a result. Therefore, with a rise in the risk-free rate of interest, the call value increases and the put value falls. Ladies and gentlemen, the change in the value of an option as a result of a change in the risk-free rate is denoted by the Greek letter rho, R-H-O, rho, and it is written as this. This is the Greek way of writing rho, R-H-O. Right, so we have almost arrived at the end. So towards the end, I will give you a little question to solve. Let us assume this is, I believe, problem number 14 in your textbook. The stock price, the current stock price is $73. And the exercise price is $65. The risk-free rate given to us is 5% in that problem. So I hardly have time, space to write the percentage sign, but you will understand. The time remaining for expiry is 6 months, which means half a year. And the standard deviation or the variability in the stock returns is 0. The question is, what is the value of a call option in this case? Now, ladies and gentlemen, do realize the fact that this stock is risk-free. Why it is risk-free is because its returns are hardly changing. The standard deviation is 0. So because there is no risk, there is no need absolutely to compute these two things. N of D1 not needed, N of D2 not needed. Why? Because both N of D1 and N of D2 are probabilities. And we talk about probabilities only when there is a risky situation. So we say there is this much chance of this happening and that much chance of that not happening, because we're not certain. There is some element of risk there. But once the standard deviation is 0, which means that the risk is 0 and we are absolutely certain about something happening, then there is no point in thinking in terms of probabilities, because they arise only when there is risk. So N of D1 is not needed, N of D2 is not needed. So therefore what remains is that call will be equal to S, and we don't need the N of D1, so we can simply subtract E and compute its present value here, and then we don't need to multiply it with N of D2 because that's also not needed. So we can just plug in the numbers. So C is equal to, let's just check what the stock price is, $73, and exercise price is $65. So $73 minus $65, and we need to discount this 65 by multiplying it with e raised to the power of minus r, where r is equal to 5%. So we write here 0.05 multiplied by time, which was 6 months in this case, so that is half a year, so I'm writing 0.5. So when you run this calculation on your calculators, you will arrive at a call value of approximately $9.60. That is pretty much it, ladies and gentlemen, for this session, and that concludes our discussion on the option valuation as far as this course is concerned. If you take a course on derivative markets, you will learn more about options, where we can talk about option trading strategies and various combinations. We can talk about, like there are some funny names there. We can create a bull spread, we can create a bear spread, we can create a butterfly spread, and we can have collars, and so many other things are there. So that would be an interesting area to explore for you if you do decide to take a course in derivative markets. For now, this is where we end our discussion. Thank you very much.